So I welcome our second speaker of this session, Professor Gergely Harcos from Alfred Rennie Institute of Mathematics, and he would be speaking on the sup-norm
That's not
problem.
my title. That's not my title. That's my title.
Yes, beyond the spherical sup-norm problem. Yes. Yeah.
Okay.
Thank you, Professor.
So this other page I put up out of nostalgia. So first of all, big thanks for the organizers to put together this online event. I was involved in organizing a similar event in last June, and I know the huge task involved. So I'm very honored to be here, and I wish already happy birthday to Balu. And as you can see, 5 years ago, I had a pleasure to be in Chennai in person in the celebration of his 65th birthday. And in a sense, the talk I'm going to give is a continuation, or at least very closely related to the problem discussed on that occasion, which was a sup-norm problem for arithmetic hyperbolic three-manifolds. So that talk addressed spherical mass forms in the eigenvalue aspect, whereas today's talk will be about non-spherical mass forms on SL2C. So my current title is Beyond the Spherical Sup-norm Problem. And in fact, I copied one page from my previous set of slides, a nostalgia page from 2015, which gives you some connections and applications or kind of motivation for the sup-norm problem. So why are we interested in the sup-norm problem? Why should we care? So first of all, the sup-norm problem addresses pointwise bounds of Hecke eigenforms on arithmetic manifolds, or more generally on quotients of arithmetic quotients of Lie groups. So pointwise bounds give rise to the sup-norm, or when the points are restricted to a compact subset of the group at hand, and the restricted sup-norm. And we would like to estimate these sup-norms, the global one and the restricted one, non-trivial. So why are we interested? There are a couple of connections. For example, in arithmetic quantum chaos, we are interested in the L2 equidistribution of eigenforms. So if you take the absolute square of an eigenform and associate to it an L2 normalized eigenform, and associate to it the corresponding probability measure, then taking a sequence of eigenforms, say with growing Laplacian eigenvalue, you would like to see that these probability measures tend in the weak star limit to the uniform distribution. And in several cases, that's celebrated theorem. So the sup-norm problem kind of addresses a complementary aspect of this problem. Namely, in the sup-norm problem, we don't want to see very high peaks, whereas in arithmetic quantum chaos, we are more interested in the average to behavior of eigenforms. And another obvious connection, once you study the sup-norm of cusp forms, you can also study other LP norms, or even more general Sobolev norm of cusp forms, and those are very interesting questions that address other kinds of value distribution of cusp forms. Now, another obvious connection is with the subconvexity bounds for L functions. A big difference being between the two problems, that in the subconvexity problem, we have a very clear understanding what the trivial or easy bound should be. That follows from the convexity principle of Fragmin and Lindelof. And by a subconvex bound, we mean a bound that is significantly better than the convexity bound. In the sup-norm problem, it's not so clear what the trivial bound should be. So perhaps it's more appropriate to call such bounds baseline bounds, but with various heuristic techniques and general observations, we can set such baseline bounds for us, and then the task is to beat them. So by and large, both the convexity bound and these baseline bounds for the sup-norm problem are those that you can address without much arithmetic. And then at a more technical level, the sup-norm problem enters bounds for exponential sums associated with Cusp forms, beloved objects of analytic number theorists, and various shifted convolution sums, say, associated with eigenvalues of the forms. And all these themes are interrelated. For example, improving subconvexity bounds, you often find yourself in the need of sup-norm bounds and bounds for exponential sums and bounds for shifted convolution sums. And vice versa, certain subconvexity bounds help us prove better sup-norm bounds. So all these topics are interrelated. Okay, enough of motivation. So let me state the main result for us. Notation throughout the talk will be G stands for the group of unimodular complex matrices SL2C. K is a maximal compact subgroup of it, SU2C, so 2 by 2 unitary matrices, and gamma will be the discrete arithmetic subgroup SL2ZI, ZI being the ring of Gaussian integers. And the result that 5 years ago on the earlier Balu Fest I presented is a joint result that appeared in 2006 but was proved a couple of years earlier, jointly with Valentin Blomer, who is here, and Djordje Mili, who I don't know if he is here, but it's very early for him, but there is a chance that he's here as well. And it says the following. So take an L2 normalized spherical Hecke eigenform on gamma left divided by gamma and right divided by K. Now G divided by K on the right is isomorphic to the hyperbolic space. So in effect, we are looking at, in this theorem, Hecke eigenforms on hyperbolic 3 space. And spherical stands for the fact that when thought as functions on the group G, they are right K invariant. And let lambda denote the Laplacian eigenvalue of phi. Well, here in this theorem, we don't need the notation nu, but already I'm indicating how it relates to the Laplace eigenvalue so that you get used to this notation. Nu is a purely imaginary number in this situation. And then for every epsilon, the global sup-norm of phi is bounded by lambda to the 5/12 plus epsilon. So here the baseline bound is lambda to the 1/2, and that has been improved to 5/12. Later, I will say a few words about, in general, at least in one, heuristics where the baseline bound might come from. But more importantly, let me emphasize that this result is the analog of the very famous, very celebrated result of Ivanets and Sarnak from '95, which proved the same kind of bound for SL2R and SL2Z. In that case, lambda to the 5/24 is what they achieved, and this result hasn't been improved since. So 5/24 and 5/12 here are very, how to say, very precise for the method we had. Very significant new ideas will be needed to improve those exponents. And I don't display in this talk, but let me mention that this result with my co-authors, Valentin, Djordje, and Peter Maga, we extended this result to more general number fields. And there we see that at real places, for the corresponding Laplacian eigenvalues, we get exponent 5/24, and at the complex places, complex embeddings up to conjugation of the number field, we get 5/12. So this theorem is a special case of a more general theorem. And also there are results by us and others, most notably by Abhishek Saha and Edgar Assing, that address the level aspect of the problem. But here, so where gamma is a more general congruent subgroup, but those aspects I will not talk about today. And then the main result for today is this very fresh theorem. So let L be a positive integer. So L will stand for which K type we are talking about. So already now let me remind you that irreducible unitary representations of SU2C have finite dimension 2L plus 1, where L is a half integer. And in this problem, in this theorem, the L's that come up are non-negative integers, and I exclude L equals 0 for simplicity. So L equals 0 is the spherical case, the K invariant case, and then the dimensions of the relevant SU2C representations are what positive integers like 3, 5, etc. I excluded L equals 0 from this discussion in that theorem, so that at the last line, where you see the bound that we obtained, the bound makes sense. For L equals 0, that bound would obviously be false. Anyway, so L is a positive integer for convenience. I is say a bounded interval, a compact subset of the imaginary axis. This will contain the spectral parameters nu for the forms participating in this theorem. Omega is a compact subset of G. That's where we restrict the sup-norm. And then we take a non-spherical L2 normalized Hecke eigenform for G mod gamma with the following conditions. So I already told you that nu lies in I. So we talk about bounded spectral parameter here. Spectral parameter is not really moving. What is moving is the K type. So what do I mean? This cusp form phi generates a cuspidal automorphic representation that you can decompose. So when you restrict this representation to K, and you can decompose into various irreducible representations of K, each representation that occurs has multiplicity 1, and they form a consecutive sequence of representations starting with some minimal one that we call tau L. So there is a minimal dimension of a K type that occurs in the automorphic representation of dimension 2L plus 1, and then also dimension 2L plus 3, 2L plus 5, all those occur. And the minimal K type that you can also call minimal weight, although my co-authors don't like this word, we assume is tau L. So L stands for the minimal weight, so to say, or L. Minimal dimension is 2L plus 1 of the occurring K types. And we assume that phi is of minimal weight in the sense that it lies in this K type, so the K translates of phi generate this K type. And then, in fact, in this minimal K type, you can consider some natural basis, and we assume that phi is a basis vector in such a natural basis, which practically means that phi is an eigenfunction of the diagonal matrices contained in K. And then this diagonal subgroup of K acts by a character on phi. Okay, so in short, we tried to consider a very natural kind of Archimedean nu form in a non-spherical cuspidal automorphic representation. And then on the next line, I would like to convince you that the baseline bound should be L for the sup-norm, restricted sup-norm, so when the points are restricted to omega, and that we are able to beat or improve to L to the 26 over 27 plus epsilon. By the way, if you have any question, just speak up. Okay, so in the next, okay, there is a slide about other results in the weight aspect, but I should emphasize that apart from the last one, Ramaker-Wakatsuki, the results are not really comparable to our result because it addresses a rather different situation, but from a representation theoretic point of view, the situation is similar. They talk about, so the first four references talk about holomorphic Hecke cusp forms on the upper half plane in the weight aspect. So Shia in 2006 for weight K cusp forms could prove an optimal upper bound K to the 1/4 plus epsilon in the weight aspect. So you can call it somewhat analogous to what we are doing, but certainly we are not finding any optimal exponent. And in fact, for the restricted version of the sup-norm problem here, the optimal exponent is not known either. So Shomo Das and Jyoti Sengupta considered the case of, so Shia's result was for the group SL2Z. And Shomo Das and Jyoti Sengupta considered compact quotients of the upper half plane coming from quaternion algebras, and there they could prove a power-saving upper bound for the sup-norm in 2015. Steiner in 2017 considered half-integral weight cusp forms, and then Kayutin Steiner could prove the analog of Shia's result and much more with a fresh new method in 2020. And the only result that's directly comparable with ours is Ramaker-Wakatsuki's very general theorem from 2020. It works for all kinds of semi-simple algebraic groups. But when you specialize their result to our situation, which is rather special, I must say, their result doesn't even achieve what we consider the baseline bound. So in the notation of this slide, they prove, now for this situation, they prove, although let me emphasize, their theorem is much more general, they prove lambda to the 5/12 minus some positive delta, and that's very far from what we consider the baseline bound, that is L. Okay, so what is this baseline bound business about? So let me here generate a very heuristic upper bound based on the pre-trace formula and its integrated version, which is the trace formula. So just very quick, let F be a compactly supported test function on the group G. And then this function gives rise to an operator. So originally the group G acts on the right on the L2 space G mod gamma, but this action of the group extends to an action of the convolution algebra that is CCG, and this action is given as written in the formula. And what's important here that this integral operator has a natural kernel that is given in the parentheses here. This kernel function, this automorphic kernel, is a sum that you can build out of F and gamma. So that runs to gamma. And now for this heuristic reasoning, we assume that RF is a positive operator that acts by eigenvalues that I denote by F at phi. It's not automatic that these eigenvalues exist, but let's assume we are in a situation where these eigenvalues exist and then they are non-negative. And phi runs through an orthonormal system of to normalized eigenforms. And so in the pre-trace formula, the pre-trace formula means that we expand this automorphic kernel spectrally, and then we evaluate it at the diagonal. So we put G equals H. So this is a technology that was pioneered by Zellberg. So he considered the spectral decomposition. Right-hand side is the kernel at G equals H, and it has the indicated kind of spectral decomposition in the situation at hand. Plus there is a continuous contribution that I suppress for simplicity. And then when you integrate both sides, then you get the trace formula. On the right-hand side, the integrals become orbital integrals, and the left-hand side, the absolute phi g squares integrate to 1. And now let's assume for this heuristic that the spectral weights kind of pick a family of eigenforms script f. So think of these weights as being the indicator function of a family, although that is very hard to achieve. But let's assume we are in this situation, and let's assume that the identity element dominates on the right-hand side, even after integrating over G mod gamma. So both in the pre-trace formula and in its integrated version, we think of the right-hand side as being F1 practically. Now, when you integrate F1 on the right-hand side over G mod gamma, then of course you get the volume of G mod gamma, and then you, on the left-hand side, you get a weighted count of these cusp forms plus also a continuous integral weighted count for cusp forms phi. So in effect, you would count the size of the family. This is how the Weil law is proved in practice. But of course, the details are more complicated because here I'm creating a situation that doesn't really exist. Anyways, we can, for a heuristic reasoning, we can think of all these conditions being satisfied, and then we get with a quotation mark that the sum of phi g absolute square of the family, so that's the original left-hand side in the pre-trace formula, that's like f of the identity element. Note that for gamma being the identity element, the corresponding f value is just f at the identity element. And then from the integrated version, we expect that that's like the size of the family of the volume. So this heuristic reasoning would tell us that on the left-hand side, each term by non-negativity should be bounded by the right-hand side. So about square root of the size of the family over the square root of the volume should be a reasonable pointwise upper bound for phi g. And then the question is how small we can make the family. Anyways, this is what I call the baseline bound. And in our situation, we look at Cuspidor representations with K-type, minimal K-type tau L and bounded eigenvalue. And then on later slides, you will see, and you probably already know, that the Plancherel density runs for such Cuspidor representations is around L square. And then we want to pick from each, we want to emphasize a single form in the K-type. So our wishful thinking is that the size of the family should be L squared. That's how many cusp forms we grab at the same time. And then the square root of this L square is L. So this is my explanation of the baseline bound L for that situation. And then we can be proud if we beat that baseline bound. So the exponent 1 should be decreased. And that's what we do. Now, one very, very interesting aspect of this project and very educational for us is that for this project, at least if you want to understand what's going on, you need to know about the generalized principal series of SL2C. So non-unitary representations of SL2C enter the picture. That's very astonishing because in all these problems, we usually don't need to see any further than unitary representation. So here I briefly summarize a convenient description of the generalized principal series of of G, which is SL2C. These not necessarily unitary representations are indexed by the complex number and the half integer, nu and p. And then the space for the representation can be described. And this is, apart from our notation, is basically taken from a very nice book by Gelf, Grayev, and Vilenkin, Generalized Functions, Volume 5 from 1966. And they say, let's take V nu P be the space of functions in two complex variables that are infinitely times differentiable with respect to both variables and their conjugates, at least away from the origin, and satisfy a homogeneity condition as displayed. And then we can put a topology on this space of functions by locally uniform convergence away from the origin, together with all their, and the same for derivatives. So this makes the space into a Frechet space, which is not too far from being a Banach space or a Hilbert space. And then, so you don't need to really remember any of this, just note that there is a natural space, topological vector space, on which the group SL2C acts in a very natural fashion. So this action should be very, very familiar to anyone who worked on quadratic forms, where usually SL2R or SL2Z is acts on the two variables. But here the two variables are complex. So this is the definition of the representation pi nu p. And then it turns out that this space admits an invariant Hermitian inner product if and only if either nu is a purely imaginary number, and that we call, so those representations constitute the true principal series, and together these representations form the so-called tempered unitary dual. But there are also some exceptional cases where the representation is unitary. In those cases, p is 0 and nu is between -1 and 1, and not 0 because that has already been put into the principal series. So those form the complementary series. So the principal series and the complementary series, so the cases in the two bubble points, form the unitary dual of SL2C, but we shall need the non-unitary cases as well. And now once you have a Hermitian inner product on your space, you can complete it into Hilbert space, and then you have a continuous Hilbert space representation. Now, we can refine this picture by decomposing the space into finite dimensional subspaces according to the action of the maximal compact. And those finite dimensional pieces can be further decomposed into one-dimensional subspaces according to the action of the circle group. That's how I call it, namely diagonal matrices inside the maximal compact. So here is how this decomposition looks like. So if the second parameter of the representation is P, then the K types that occur in the representation they correspond to L, at least absolute value of P. So once again, the Lth K type has dimension 2L plus 1, but L is not necessarily an integer. It can be any half integer that's congruent to P mod 1. But in our situation, so the representations that occur in the automorphic L2 space, L2 G mod gamma, all these parameters will be actual integers, not half integers. And then for an L piece, which is a finite dimensional piece of this representation, it has dimension 2L plus 1, and you can find the natural basis according to the various characters of this subgroup, and those characters. So they are of the characters that enter here are of the form e to the 2qi rho. So you raise this parameter to 2q, and q must run from -L to L, and there are 2L plus 1 such integers or half integers. And then they really define these one-dimensional pieces for us. And so in our original problem, we are interested in a phi that spans this one-dimensional, this very one-dimensional piece. That's what we are interested in. And now something very interesting happens when you ask yourself how these representations are, these generalized principal series representations are irreducible. So it turns out when nu is not a half integer, then the representation is irreducible and isomorphic to flip the one you get by flipping nu, the pair nu p to its negative. And if nu is a half integer, that the conclusion still holds true when absolute value of nu is at most absolute value of p. And then there is some very interesting exceptional case that is relevant for us. That's what I'm telling you about. If nu is half an integer and absolute value nu exceeds absolute value of p, then they are both reducible. That's already very interesting. Now, without loss of generality by symmetry, you can assume that nu is positive. Then in V nu PL, the K types that correspond to L less than nu, and then also necessarily at least absolute value of P. So these finitely many K types together form, they span a closed invariant subspace. It's finite dimensional actually invariant subspace of V nu P. And when you take the corresponding quotient, that's irreducible. On the other hand, for V minus nu PL, the other guy that we need to examine here, the K types with L at least nu form a closed invariant subspace, and that's infinite dimensional, and that the restricted or induced representation on that invariant subspace is irreducible. So in one case by a quotient, in another case by passing the subspace, we get an irreducible representation, and both of these turn out to be isomorphic. Both of these turn out to be irreducible and isomorphic to p nu and p minus p nu. So look what is happening here. We started with parameter nu p and minus nu p, and after a small surgery that we make on the spaces, we end up with representations isomorphic to p nu and p minus p nu. So there is an almost symmetry when you flip nu p to p nu. The two representations are very close to each other. More precisely, if you look at this decomposition and you take the space of endomorphisms, just vector space endomorphism of the space on the left-hand side. So take endomorphisms ring of V nu P, then because of this decomposition, that endomorphism ring comes with a block matrix decomposition consisting of blocks hom of V nu P M and V nu P N. And when you restrict this block decomposition, when you only look at blocks with indices at least absolute value of P and also absolute value nu, then in the representation for nu P and P nu and also minus P nu and minus nu P, so in all these four representations, the group will act in the same way in those spaces, in those block matrices. And this will have a dramatic effect for our problem. Now, I still need to build up some theory for this project. There is the wonderful seminal work of Gelfand and Naimark, two very, very substantial papers from 1947 and 1950, which generalize the phenomenon that, so from finite group theory, you know that the group algebra CG is isomorphic to direct sum of full matrix algebras. So this theorem can be generalized to this infinite group, Lie group G equals SL2C. Namely, they showed that there exists a Hilbert space isomorphism. L2G is isomorphic to essentially an integral over the tempered unitary dual of G. So here I spelled it out in very concrete form. I made the integral and sum on the right-hand side so that ITP pairs exhaust the principal series, and apart from t equals 0, where 0p and 0 minus p are equivalent representations, each representation occurs with multiplicity 1. And for t equals 0, the measure is 0, so that is it's like those doublings were not even there. So the L2 space of G decomposes to these full infinite dimensional matrix algebras, endomorphisms of VITP with respect to measure that is proportional to t squared plus p squared times the Lebesgue measure for t. And you can, the actual constant of in front of this density is depends on the core measure you use on the group G, and so we can just pick a core measure where t squared plus p squared dt is the Plancherel measure. And what's amazing that if you look at a function on the left-hand side, say initially compactly supported smooth functions, then the corresponding operators in these various endomorphism pieces are fully independent. And there is a Plancherel theorem which says, well, not fully independent, but there is of course an obstruction. The Plancherel theorem, these for each piece in the corresponding endomorphism ring that I call pi f here, the relevant norm for the Hilbert subspace is the Hilbert-Schmidt norm. And so on the left-hand side, so there is a Pythagorean theorem which says that the L2 norm of f squared is the integral of the various Hilbert-Schmidt norm squares that come from pi f when you integrate against the Plancherel measure. But apart from this joint square integrability, you can choose, as long as you are happy with a function in the L2 space, you can choose any action of your function in the various pieces. And here I emphasize compactly supported smooth functions on G because they form a dense subset of the Hilbert space on the left. And for such test functions f, the corresponding operators, so the things you see inside these endomorphism pieces are trace class operators. And there is an inversion formula. You can reconstruct Fg from these species by taking the traces like here and integrate against a Plancherel measure. So here there is really a transform given by pi f and an inverse transform, and you can extend these transforms to the full L2 space, and then you get an isomorphism. In particular, there is surge activity here, which is very important. Now, I'd like to introduce, starting from this picture, the generalized spherical transforms. So for a fixed L, as in our theorem, we'll be interested in test functions f, which have the following property. So the corresponding piece on the right-hand side should act by a scalar on the Lth k-type component and by 0 on the other k-type component. So remember, we had this decomposition. This is an orthogonal decomposition of the space. And we want to see a scalar action on the Lth component and the 0 action on the other components. And one can identify easily what these functions correspond to on the left-hand side. They form a Hilbert subspace defined by these two conditions. So the function should be k-central, so it commutes with the action of k. And also, if you look at 2L plus 1 times the character of tau L, so that convolution by the conjugate, convolution over k by the conjugate of that character corresponds to projection on the Lth k type. F should be invariant with respect to left and right convolution. So this is the function theoretic description on the left-hand side of what we want on the right-hand side. So instead of general actions in the various endomorphism pieces, I want some very simple actions. So in effect, I want our pi f to favor the Lth piece and Lth k type and forget about all the k types, and I want a very simple scalar action. And then this scalar can be actually calculated. We talk about a scalar action on a space of dimension 2L plus 1. So then the scalar can be identified, of course, as the trace divided by 2L plus 1. I mean, if you act by a scalar on a space of dimension 2L plus 1, then the trace is 2L plus 1 times that scalar. And the trace itself can be calculated just by plugging in as an integral of fg times what we call the spherical trace function. So the spherical trace function is defined from the group action in a straightforward way like this. Although this definition is a bit abstract, and later we'll have to see more concrete descriptions. And then the previous inversion formula that I indicated here gives rise to an inversion formula here as well. So we have this spherical transform that is the trace, and you integrate with respect to the Plancherel measure the spherical trace function, you get back fg. So that's a special case of this very general Gelfand-Naimark theorem. And again, we have surjectivity, and there is a Plancherel formula. So you can easily calculate the Hilbert-Schmidt norm of these scalar acting transformations. Well, what is it? So 2L plus 1 times the sum of squares and the diagonals. So that would be 1 over 2L plus 1 times the absolute square of that. You integrate with respect to the Plancherel measure. That's the L2 norm square on the left-hand side. So again, there is a surjectivity phenomenon, and this L2 condition is the only obstruction, as long as you are happy with L2 function satisfying this conclusion. But then later in practice, you want to take rapidly decaying test functions f, and then it's not so straightforward to see what kind of transforms those have. Now, the spherical trace function was defined in the abstract, but it has a very concrete integral representation. At G, you have to integrate over K, kappa L, K inverse GK, where kappa L is given by this very simple-minded function from the matrix entries of the matrix. But note that kappa L, so this simple-minded expression has to be applied not on G, but K inverse GK, and then you integrate over K, and then things become complicated. It turns out that this function extends holomorphically in the new variable, and it also satisfies a soft general bond that we skip here. And then it turns out that the spherical trace function has some remarkable symmetries. So there is symmetry with respect to G, and there is also symmetry with respect to the parameters of the representation. So this right-hand side formula follows right away from the definition. The left-hand side saying that it is real valued is more accidental, reflecting that basically that in the Cartan decomposition, the middle piece, which is a diagonal matrix, or 1 over or 1 and 3 determines the other because of the determinant 1 condition. That's vaguely, well, the actual proof is deeper than that. But for usual spherical function, that's actually a proof. But what's really remarkable, and you can find, and the source of that is that I already explained to you. It is really an application of that. that when you flip nu and p when you can, so that nu and p are congruent to mod 1, so nu is also a half integer, then you get the same spherical trace function, as long as L is sufficiently large, larger than either of the two parameters. So that's very amazing and shocking, as you will see in a moment. Because then by the previous two slides, if the function f decays rapidly, then if we scroll back, the spherical transform was cooked up from the spherical trace functions with this fg. Then all these symmetries possessed by the spherical trace function in the new p parameters will be inherited by the spherical transform. So it says that on the one hand, the spherical this generalized spherical transform f hat extends holomorphically in the new variable, and it satisfies this symmetry. And that means that nu and p are not independent as we thought. So, for example, we want to emphasize p equals L and neglect p less than L. But that means that if you plug in, say, L for nu, then we want to neglect f hat LP, but that means we also have to neglect f hat PL. So at the Lth piece, we create many zeros, and that causes all sorts of troubles. I think this is all too fast, but you can review the slides. I will put them on my webpage, or you can review the video. But this really causes a problem for us when we try to select the Lth piece, Lth k type from our representations and not the other types. And as I told you already that we want a rapidly decaying test function, and ideally we would like to use a compactly supported test function, for which case Wang in 1974 characterized the possible transforms f hat that these f's correspond to. So this is an analog of the Pelly-Wiener theorem, and it says that in this HTL space, f is smooth and compactly supported if and only if this transform not only extends holomorphically and satisfies these symmetries, but also has rapid decay in vertical strips. And then it's a very precise upper bound, which depends on the support of the function. And we found this theorem too restrictive for our purposes. Namely, we couldn't quite find the test function that satisfies both star and this very strong upper bound for the transform. Namely, this exponential was too small for us. So in other words, we couldn't really make our test function compactly supported. And so we generalized Wang's theorem to what we can call the Schwartz class subspace of HTL. So if you are happy with going not with compactly supported functions, but with functions of rapid decay along with their derivatives, then we don't need the transform to be that precisely decaying in vertical strips. It is just sufficient that it decays with some implied constant rapidly in vertical strips. And so this generalization of Wang's Pelly-Wiener theorem was very useful for us. So in the end, we settled with the following test functions, settled for the following test functions in HTL. We define the function in terms of its transform. So we prescribe on the spectral side the weights in advance, and we settled for these Gaussian weights. So this transform function satisfies all the conditions. So item 2 in this theorem and also star. So on the function side, f is smooth and rapidly decaying with derivatives. And this does provide a positive operator RF on the automorphic L2 space, which puts about 1 over L weight on the V nu LL component with bounded nu and a negligible weight on all the other components V nu PM. So note that when M is distinct from L, already we put weight 0 because that's how we created this function space. So for M not equal to L, that is already out of the game. And if P is not equal to L, then P is strictly less than L, which makes this function exponentially small. That's what I mean by negligible. So at this point, we found a spectral weight function with rapidly decaying test function, which emphasizes the Lth k-type for those representations where L is the minimal k-type. And then when we pass from F to its Fourier coefficient, so when we average F, we integrate over the circle group against the character, and this Q should be chosen in the same way as our original cusp form in our original theorem, which was here. So here I said phi is an eigenfunction of the matrices, so that selects a character of the circle group, and the same character has to be used for this averaging process. Then when we pass from F to these Fourier coefficients, then we still get the positive operator, which now puts about 1 over L weight on the one-dimensional components, V nu L L Q, with bounded nu that occur within the automorphic L2 space, and a negligible weight on all the other one-dimensional species. So at this point, in 3 steps, we are down to emphasizing one-dimensional species in cuspidal automorphic representations occurring in L2 G mod gamma. First, we went down to P equals L, then we went down to M equals L, and then we went down to R equals Q. So in 3 steps, we are now seeing in the spectral, on the spectral size, this single one-dimensional spaces, one of which contains phi. And I only have a few minutes left. I planned for a 60-minute talk. But the upshot is that F itself from the inversion formula, sorry, I'm trying to find, F can be expressed by the inversion formula for the prescribed spectral weights and the spherical trace function. And then now we average F over, so we take its Fourier coefficient, Q Fourier coefficient over the circle subgroup. So in effect, that's the same as taking the Q Fourier coefficient of the spherical trace function. So at this point, things get really difficult from an analytic point of view, because already the spherical trace function was a difficult analytic object. And now we find ourselves in the need of taking its Q Fourier coefficient. So the already complicated object is integrated like this. And we have to analyze, we have to estimate this Fourier coefficient, Q Fourier coefficient of the spherical trace function. Namely, by using a standard amplifier, we can finally bound our cusp form squared at G by such an expression, where by amplification now gamma doesn't run through SL2Z, but all sorts of 2x2 matrices with Gaussian entries. And for such a gamma, we can scale down gamma to gamma tilde so that it lies in SL2C. And then there are certain weights coming from amplification. And then we conjugate gamma with G as in the pre-trace formula. And the upshot is that we need to understand the sup-norm for all these conjugated gammas when scaled down by that determinant, square root of determinant. And we have good control over the weights coming from amplification. So X1, capital is the amplifier length. It's a parameter at our disposal. X1 is bounded by capital N. Xn is supported on product of 2 special split Gaussian primes or their squares, and there Xn is at most 1 and Xn is 0 otherwise. So we have a very concrete upper bound for phi G, pointwise upper bound in terms of this averaged spherical trace function. And this leads us to analyzing the Q Fourier coefficient of the averaged spherical trace function. And let me tell you that this is a rather difficult task. So we found that the best way to analyze it is to put G into Cartan form. So we represent G as K1 from the maximal compact times diagonal of R and 1 over R matrix, and then a K2 from the maximal compact. So that already introduces us 7 variables, because the maximal compact we parameterize by 3 Euler angles. And then when you look at the definition of the spherical trace function, that involves an integration over SU2C. That brings in another 3 variables for integration. So we have to jiggle with these 10 variables. And so that's a bit scary first. But then by rather straightforward manipulations, we end up with an expression which, after the triangle inequality, gives the following upper bound for the average spherical trace function. It's something very concrete, where ABCD abbreviates certain functions which are of absolute value at most 1, and in fact a squared plus b squared equals c squared plus d squared equals 1. And then from Young's inequality, very carefully examined as Stirling's formula, we already see that the integrand inside is over 1 over something. But of course, depending on Q, this something can be as large as 1. And in the best case, it is 1 over square root L, which is still very far from sufficient for us. Essentially, we want an upper bound of 1. And then we examine when we can improve these bounds. And we find that the contribution of very small t or very large t is negligible, because then this factor is very small. If t is not too small and not too large, so that this denominator here is sizable, not too close to 0, then because of the nth power, negative nth power, the contribution of the second factor is negligible unless r is very close to 1, or is the middle Cartan coordinate. And then we analyze this inner integral, and we see that unless phi and t are in a very special constellation, this integral is very small, and this forces G to be close to diagonal. So in the end, we get this very clean, but it involves hard work, upper bound for the averaged spherical trace function. So we have essentially a bound 1 always, and when G is somewhat away from the maximal compact or somewhat away from diagonal matrices, then we have better upper bounds. And then we got to the end game, and maybe I have 1 minute left. So we estimate carefully, going back to amplification here, we estimate carefully. Oh, Valentin, hi. And we estimate carefully the number of matrices whose determinant is of a given type, either 1 or product of 2 Gaussian primes or their squares, and we control how far the corresponding conjugated version of gamma is away from K and D. And in the end, we get a bound for phi G like this. Here we have dyadic ranges for the 2 kinds of distances. And we can, it's not hard, upper bound at this point, the dyadic sum by L inverse 1 over L, the amplifier length, and L square L to the minus 2 over 9. And so we win the optimal choices at the 2 over 27, and that yields our final estimate. And sorry, I had to rush through a little bit at the end, but my last slide is identical to the last slide of my previous talk 5 years ago. Happy birthday, Balu! Many more beautiful theorems and years to come. Thank you for your attention.
Thank you for the talk. So we still probably have time for one question. If anybody has a question, please unmute and ask. Okay, if there are no questions, then we thank the speaker.
Thank you so much for having me. Thank you. Wonderful conference. Thank you so much.